All right, it's the last lecture for Chapter 8. We want to decipher between elimination and substitution. Let's see if we can kind of wrap it up with some tips for you. Again, there's no magic, no silver bullet that allows you to just know you got to practice and work on these things. But how do we know? How do we decipher between these four different mechanisms? Okay, so big picture, substitution versus elimination. A little deeper, you know, SN2 or SN1. So I'm going to loosely follow section 8.11. I'm going to divide it up a little differently. Give you some principles. Good nucleophile, but weak base. Favor substitution. Makes sense. Substitution nucleophilic, so we're talking about. You got sodium bromide. It's a primary, so if it's going to substitute, it's going to be SN2. We talked about sodium acetate. Let you fill in what these are. Okay. O minus. Draw that acetate out. There you have the product. Okay. And we'll talk about this stuff in class probably as questions come up. But this is resonance stabilized. The same reason it's a weaker base than a localized O minus makes it a better nucleophile for a less sterically hindered alkyl bromide. Okay, there's so much nuance here. Okay, you just have to keep working at it. So another delocalized O minus that we haven't talked about as much. It's a double bond there. Is sodium we call phenolate. And that is the deprotonated form of phenol. It's a special kind of alcohol. You could draw resonance forms of this all around the ring. Okay, it's delocalized O minus, same thing. So any O minus that's delocalized, we're going to treat it as a little bit weaker base than a localized O minus. It's kind of a way to think about it. And up to this point, the only negative charged anions that we've used as bases are oxygen primarily and nitrogen. Okay, if nitrogen is negative, it's even a stronger base than oxygen. So this is sodium cyanide. So a negative charge like this is not that strong of a a base. So we're going to treat it as a nucleophile. Okay, and to be consistent, we're only showing this as a triple bond as a nucleophile. You can also use an alkyne as a nucleophile, something like that. We'll see. That's a nice way to make a carbon-carbon bond. Okay, that'd make the exact same thing, but it'd be a C-C triple bond. Okay, so we haven't used any of these as bases. Okay, and we won't. And a neutral amine that is not DBU, DBN, a neutral amine, not DBU, DBN, can undergo SN2 as well. Okay. And you generate, in the case of nitrogen, okay, a salt. Okay, nitrogens that are neutral give the salt product. This whole thing is the product. And that's one kind of guiding principle. Two, I've said this one before, large sterically hindered or bulky non-nucleophilic bases favor E2. They favor elimination by E2. Okay? They cannot act as a nucleophile. So let's show some examples of this. Even though this is a primary, we're going to use a primary here to make the point. Even though it's a primary, we're using bulky non-nucleophilic bases. Potassium terbutoxide gives the product. DBU. Again, I would give you the structure, but for an exercise, you can go back and find those structures of DBU and DBN. They're also in the text. DBU, DBN, they all give the same product. LDA is another one. That's LDA. Same product. Okay, so the same product in all these cases, but I'm just reviewing these non-nucleophilic bases. Let's give some other rules that are pretty hard and fast. Tertiaries. What do we know about tertiaries? They cannot undergo SN2. So if they can't undergo SN2, yes, they can still undergo substitution. What happens if they're mixed with something strong? It's going to be a base it's going to eliminate. Okay, it's too sterically hindered to go SN2. Number 4, primaries and methyls. What can they not do? Cannot form carbocations. As you practice problems, you keep learning about these things, you'll see that's going to help you, okay? Those carbocations are not stabilized enough. There's not enough alkyl groups to stabilize them. So therefore, what can you not do? No SN1 or E1. So let's go through carbocations. Let's do a couple case studies. We're going to see there'll be times where there are mixtures. Let's look at primary alkyl bromide. We treat this with a strong something, sodium hydroxide. Okay, in principle, it's strong, so it could go SN2 or E2. And what I want you to sort of remember is that for elimination reactions, what happens? The trend increases with more steric hindrance. So you can eliminate with an primary, but it's not favored. Okay, a primary is much more favored for SN2. Why? Because that transition state can be accessed. So the less sterically hindered, the more favored SN2 is. So you're going to get SN2 in this case. Same idea with sodium methoxide. We're going to get an ether. Oops. Get that product. It's called an ether. Talk about that in chapter 9. However, when would you get E2? When you have a bulky non-nucleophilic base. Even though primaries are not as favored, it cannot undergo SN2, so therefore what happens? Eventually you get to that. Maybe you have to heat it or wait longer or whatever. Same idea. DBU will also give you, because it's not a nucleophile, it's too bulky, non-nucleophilic bases give you E2. Let's look at some secondaries. Secondary alkyl bromide. We're going to treat with KOH. That's a strong something. And there'll be times where we get mixtures. Because it's a secondary, it's kind of in the middle, we would assume we get a mixture here. SN2, E2. Potassium terbutoxide, however, gives you only E2. What happens when you have H2O excess? That's a weak something. It's going to function as a base and a nucleophile. Same idea. You get the same products you got over here, but this is formed by SN1, and this one's formed by E1. Another example of a non-nucleophilic base, LDA. What happens? You get only elimination. Okay, so hopefully you're seeing some patterns. Keep working through them. Tertiary, do one more case study with a tertiary. Got a bromide, 3 methyl groups, so it's a tertiary. We're going to treat that with sodium hydroxide. Strong something, what we say tertiaries cannot undergo SN2, so there's no way you can get substitution. You're only going to get the E2 product. Okay. Again, E2 and E1 products look the same. We want to understand the mechanism, same as substitution. Same idea, NaOCH3, same type of product by E2. What happens when we add water? Excess, it's the nucleophile and the solvent, or the base and the solvent. We are going to get both. Why? Because we're going to get carbocation. You get the alcohol from SN1, and you get the alkene from E1. And finally, even though you get the same products with sodium hydroxide and sodium methoxide, potassium tertbutoxide really guarantees that even more so. So you get the E2 product. Okay, so these are all just examples to give you a little bit more and more comfort. Okay, we'll work some problems in class. Now we're at the stage where we can just work lots and lots of problems, answer questions during our time in class. We'll have several lectures for each chapter to do so, and the next set of lectures is chapter 9. We're going to see the same principles. We're going to see a substitution and elimination, but we're going to start with alcohols. So instead of forming alcohols, we're going to start with alcohols as our starting materials. We're going to protonate them with acid. Okay? So really, chapter 6 was an intro. 7 is really key to get that down. Once you get 7, you work through chapter 8, and then you kind of bring those two together, and then you move on to 9, and then you keep reviewing. We're in the thick of it. This is very difficult stuff, so keep at it, study hard, and that finishes chapter 8.